starting our first, training course in Tsunami-HySEA, and for the very first time also in Meteo-Tsunami-HySEA, and these 2 days. And I don't know if you are aware that we did already some weeks ago a training course within the umbrella of GeoInquire project. In that case, the course was devoted to a very brief and easy introduction to Tsunami-HySEA code, and in the second day to installing the basic version of the code in your local computer or also in the cloud. So for those of you that are interested in these two topics, I encourage you to have a look through the GeoInquire webpage and look through this content. Also was recorded, and there's the material available for you. So now the subject for today is going a little further in Tsunami-HySEA code, dealing not only with inundation propagation simulation, but also performing high resolution inundation that require the construction of nested grids. That is, a critical issue. So for this first part of today, we have Carlos Sanchez from the University of Malaga that have prepared some slides. Again, all this material will be available after the course, and also the recording. And we will learn today how to perform this high resolution inundation. For tomorrow we have for the very first time, as I said, Meteo-HySEA, because it's a code that we are developing within the framework of ChEESE 2 project. And we will have Clea from IRB in Croatia doing an introduction to meteo-tsunamis, as far as I think. And in the second part, we will have Alex Gonzalez from the University de Malaga, who is working in developing this Meteo-HySEA code that, starting from our experience in HySEA codes, implement the effects of the pressure, winds, and so to perform this meteo-tsunami simulation. I don't want to take more time, and after that brief introduction, I'm giving the floor to Carlos Sanchez that will do this short, brief, one-day introduction to Tsunami-HySEA. Carlos,
Okay.
what do you want?
Thank you, Jorge, for the presentation. Let me share the screen. Okay. Just okay. Okay, so I think you can see my screen, right? Okay. So yes, you can see the first slide.
Yes,
right?
we can see it.
So thank you very much. Hello everyone, and thank you for being here. As Jorge mentioned, okay. As Jorge mentioned, my name is Carlos Sanchez. I'm professor here at the University of Malaga and member of the EDANIA team for the past 10 or 12 years. So, well, I cannot consider myself among the youngest members, but neither among the veterans. So, jokes aside, welcome to this introduction course about Tsunami-HySEA. Well, we will see later that it's not so introductory course because, well, my intention today is show you how to set up and perform tsunami simulation, not only the easy examples like propagation in small domains, but more advanced setups like real big domain simulation, saving time series, pre-processing with the building of nested meshes, inundation simulation, and a bit of post-processing analysis of the results. So let's start. This is more or less the outline for today. A small introduction about the Tsunami-HySEA model, some tips about installation on a HPC machine. We will work today on a small cluster in order to show you how to proceed with these tsunami simulations. And we talk about the main ingredients that we need to perform a simulation, and a kind of hands-on session, not literally hands-on, but I will show you some examples from propagation to high resolution inundation. Okay, so let's start. Let me start talking about tsunamis, what they are, and which are the main difficulties in its modeling and the numerical simulation. As you know, tsunami are unpredictable events and catastrophic in their potential for destruction of human lives and also the economy. And this unpredictability of their occurrence is, let's say, a challenge to the tsunami community because it's very difficult to obtain from the tsunamigenic records an estimation of the recurrence rates and also the severity. So accurate and efficient mathematical and computational modeling is necessary to provide tsunami forecast and hazard assessment. So tsunami simulation in the framework of tsunami early warning system, let's say it's a quite recent achievement, but it's still limited regarding the size of the problem and restricted at the moment to tsunami wave propagation. So because faster than real-time simulation require greatly improved and high efficient computational methods to achieve extremely fast and effective calculations. So this is very important to use HPC resources to achieve this challenge. Okay, here you can see we can introduce the Tsunami-HySEA models, which approximates the non-linear 2D equation for shallow water in this case in longitude and latitude coordinates. The shallow water equation written in these spherical coordinates are displayed here. We will now go deeper into the specifics of this equation in this course. Instead, we will focus, as Jorge mentioned earlier, on the practical application and the results of the use, more or less, of the use of Tsunami-HySEA. Okay, so let's move on to explore the capabilities and more. Just a couple of slides showing the numerics aspect of the model, highlighting, for example, the model's high order accuracy. This is well balanced at, let's say that it's efficient computational implementation on GPUs. This will be an important side of the problem. We can say that we also enrich the model with other nice numerics properties. We use a hybrid finite difference and finite volume scheme. We use a staggered leapfrog type scheme for the propagation part and a flux limiter TBD-WAF type scheme for the inundation part. Again, I'm not going into the numerics details, but this model, the scheme presents a high level of parallelism and scalability. This would be very, very important. And let's, in this slide, let's highlight some key features of the Tsunami-HySEA model. For example, the seabed deformation model. We incorporate the CADA model for the seabed deformation, allowing for the the instantaneous transmission to water-free surface. Tsunami-HySEA model supports multiple Okada segments, synchronous or asynchronous fracture, and several filtering techniques. And additionally, it works for rectangular, but also with triangular faults. Okay. As I mentioned before, it is massively parallel. The model is designed for parallel computation using CUDA and MPI, allowing efficient utilization of GPUs and multi-GPU setups, and another capabilities including nested meshes, 2D decomposition with load balancing, direct output of time series, resuming store simulation, and the input output files saved or stored as netcdf formats. We will see later the thing of these output files. And this is the workflow in case of the occurrence of a tsunami event. First, we are able to obtain some parameters of the source, given, for example, by detection sensors. We know the magnitude, more or less the location. we can estimate the Okada parameters, and in our side, we are able to set up our computational domain and perform the simulation. Then we obtain the result and all the stuff with the post-processing analysis. More or less, this is the workflow. Okay, so, well, I would like to spend some time discussing how you can install Tsunami-HySEA on an HPC cluster, such as, for example, the cluster Picasso in Malaga, the Power 9 at the Barcelona Supercomputing Center, Cineca machine in Italy, or similar facilities. So I will try to demonstrate the installation process using the source code of Tsunami-HySEA. I mean, the installation of the compiling Tsunami-HySEA from the scratch, from the source code. I'm going to demonstrate the installation on Thika. Thika is a small cluster of the Andalusian supercomputing network here in Spain. Thika, sorry, Thika only has 6 GPUs, but it will sufficient to illustrate how to launch simulation and get started with Tsunami-HySEA. So we are going to connect Thika, and I will show you how you can install Tsunami-HySEA from the scratch. So let me access Thika. Okay, so in this, you see my screen, right? I'm going to access the cluster. And I'm going to take a while. Okay, so I'm into the cluster, and as you can see here, I have several folders. One is projects, the other one is software. I'm going to access to software directory, and you can see here different versions of Tsunami-HySEA. I'm going to work with the latest one, that is 4.3.0. But in order to show you how to install, I'm going to remove this one that I recently created for this course. I'm going to remove this folder. Okay. And I'm going to install or compile Tsunami-HySEA in this new folder from the scratch. So I'm going to create again this folder. I'm going to name as HySEA version 4.3.1. And I'm going to allocate here the Tsunami-HySEA source code. These two folders contain the source code for compiling Tsunami-HySEA and also the source code for the load balancing stuff that we will talk about this later. So I'm going also open FileFilla. You can use terminal commands to transfer files, but it's easy for me to show you how you can upload directly to your HPC account or wherever the source code of Tsunami-HySEA. I'm going to upload to the recently created folder. It takes a while. And the first thing that you should do in before compiling the version of Tsunami-HySEA, here we have the source folders. And then you need to load some modules that are necessary. Okay, so first we have created the HySEA folder, and then we need to load some modules that we need prior to compile the version. Okay, so first I'm going to remove or purge all the module list. Sorry, module list. So we have no modules load, but in order to compile, before compiling, we need to load the necessary modules, including module load CMake, should be one of the modules that we need. CMake 10, for example, okay. we need to module load also net CDF. In this one is if I remember well, yes. Net CDF. We need to load module load parallel net CDF. Okay. We also need to load module load OpenMPI. OpenMPI, I think it's version 4, if I remember well, yes. OpenMPI and also CUDA. Okay, so these are the modules that we need to load before compiling. Module load CUDA. CUDA, I think the version 9. Okay. So if we, let me clear in order to show you better, clear module list. These are the modules that are currently loaded, okay? And additional, we will load also Python in case we need for processing tasks. Module load Python version, I can't remember the version, this one, okay. Okay, so we have all the modules loaded in order to compile the Tsunami-HySEA. So we are now in this folder in where we have the source code. Okay, we are going to create two folders to allocate the compiled version of the executable of Tsunami-HySEA. We have need to make dir bin and make dir bin LB, which means load balancing. This one to allocate the Tsunami-HySEA executable. This one to create or compile the get load balancing binary file. Okay. And this is very easy because if everything works, we move to the bin folder and then just we run cc make and point to the source folder. Okay, just type here and we open this kind of interface. We type C in order to configure it. Everything should be detected by the files. Again, configure, sorry. And at the end, we are going to generate the files, okay? And after that, we have here just the make file, and we can just compile by using, if you prefer, clean before, and then make. Make should compile the Tsunami-HySEA and obtain the executable of Tsunami-HySEA. Okay, we will do in a while the same thing for the bin LV to create the get load balancing executable. We will see later we need this bin file in order to say how we can manage the GPUs, the different GPUs, in order to divide our computational domain into several GPUs. And it takes a while. We are going to wait for a while. And at the end, we should have in our bin folder the executable of Tsunami-HySEA. Let's wait for a while. It takes a bit. Okay. So at the end, after 10%, we have just built the Tsunami-HySEA executable that is here. Okay. It's very easy. And the other thing is to move to the bin LB directory, and here just do the same, cc make dot and point to the folder of the source code of the load balancing script. This you will get an error, but we do the same, configure again, and then generate. And after do make, you will get an error, but it's easy to fix because we need specify the version of the compiler for C++. We just copy this and we are going to edit the file cmake patch.txt. We are looking for this flag cmake. We go to the after the equal, and then we paste the std equals C++11. Okay, we save this modification, and again we compile with the make command, and after that we build the target get load balancing executable. Okay, so at the end we have two executables, Tsunami-HySEA, that is the main executable to do that, and also the get load balancing that we use to manage the use of the composition of the computational domain to several GPUs. Okay, so this after that we have just compiled the Tsunami-HySEA. Okay, so let me go back to the slides again. Okay, so all right, so once we have Tsunami-HySEA installed on our machine, in our case on an HPC cluster, how do we go about launching our first simulation? What are the main ingredients that we need? Okay, so start talking about the inputs. And one of the main ingredients is the bathymetry or topobathymetry files required for Tsunami-HySEA simulation. Okay, so about the file format, we just say that bathymetry file that contains X and Y coordinates, in this case, longitude and latitude coordinates of a given domain, and also the corresponding elevation. Okay, it is stored in GRD format, which follows the standard NetCDF4 data model and file format HDF5. Okay, and about the data precision, the variables longitude and latitude are stored in double, should be stored in double numerical precision, while the bathymetry data, the elevation variable, is stored in single precision. Okay, and just to say about the tools that we can use, GDAL, if I remember well, is the Spatial Data Abstraction Library, is a kind of a translator library for raster and vector geospatial data formats to to work with these topobathymetric files effectively. Okay, so after in a while we also load the GDAL library into our cluster environment. Okay, the second main ingredient is the par file. The parameter file is a text file with the list of the parameters needed for the simulation. Okay, we need to specify, we will see later in a while, we need to specify the inputs data, the parameters for the initial condition, another thing like simulation times, output variables, and other, let's say, coefficient intrinsic to the model. And as I said, we will see later specifically what there is in each line of this file. Okay, so main first ingredient, the bathymetry, second ingredient, the parameter file, and as the third, the last main ingredient is the file in charge of managing the load balancing for the GPUs or GPUs, depending if we are going to use one card or more than one. Okay, so we need also this binary file generated by the script get load balancing that have just compiled in the cluster. Okay, so these are the three main ingredients in order to perform our first simulation. Okay, so let's go a bit deeper into the parameter file. This is an example of one of the parameter file, but as I mentioned earlier, how do we know what to put on each line of this parameter file? Well, to find out, let's return to the Fika cluster and take a look. Okay, let me go back again to the Pika cluster. I'm going to move to the bin folder. Okay, so I'm going to move back, cd bin, and here you can see the executable of Tsunami-HySEA. Okay, so if we launch Tsunami-HySEA like this, Tsunami-HySEA with no arguments, followed by no file, okay, we obtain how to fill this parameter file. Okay, so I'm going to just run this command with no arguments, and as you can see here, let me put a bit larger this. As you can see here, you have a header of Tsunami-HySEA, which appear here, Daniel Research Group, University of Malaga, blah, blah. And then it's explained how to fill this second, or this first argument for Tsunami-HySEA. So we need to perform Tsunami-HySEA followed by the parameter file. And how we can fill this parameter file? Well, we just follow this list, okay? So we need to specify the bathymetry name. Is a kind of the name for the experiment, for the event or whatever. Then the path to the bathymetry file. And then we need to choose one of these 7 options about the initialization of states. Let's say the initial condition, okay? So if we want to provide the sea surface displacement profile, we put here 0. If we use a standard Okada parameters, we put here 1. Or if we want to provide Okada but directly from file instead of list the parameters, we provide a file with all the parameters from Okada. We use also triangular Okada faults, triangular Okada from file, and also we can provide sea floor deformation from file, sea floor dynamic deformation from file. We will see later the difference between these 2 options, and also Gaussian as the initial condition. Depending on the initial condition that we put here, we need to specify after that different parameters depending on this, on the initial.
Carlos, I have a question for you. May I?
Yeah.
Which is the difference between the option 0, sea surface displacement, and the option 5?
Well, the option 0, you need to provide the deformation applied to the floor. Okay, so you need to put in your GRD format the let's say the bathymetry resulting from this deformation of the floor, and here you just need to put the initial condition of the free surface. Okay.
So at the end in the at the end in the from the people listening, at the end it's the first one, the 0. You just put the sea surface deformation, but you don't change the bottom.
No. Yes.
Sea surface deformation. So you have a kind of perturbation in the seawater surface.
Yeah.
But in the 5th one, you move the bottom, so it's more related like an earthquake take place. You move the bottom, and that is transmitted to the sea surface.
Yeah. In the case of 0, you maintain your original bathymetry.
That's right.
And in option 5 or 6, you obtain a kind of deformed bathymetry. Okay. This is more or less the main difference between that. Yeah, can I follow?
Yeah, continue. Yeah, it's if I see that the audience is a bit shy, I will try to make question myself.
Okay.
Big doubt that I may have.
Okay. Perfect. Okay, so after specify the initial condition, as I said before, you need to specify the different parameters for each of these options. Okay, so if you choose 0, you need to provide the initial state file, the file containing the initial state for the water surface, as you said before. If you choose one, you are considering a standard Okada, so you need to specify if you want to apply Cayura filter to the Okada deformation with 0 for no, 1 for yes. If you choose one, you need to provide the depth in meters to the Cayura filter, and then you need to provide the number of faults, and for every fault, a line containing, in this case, the time, because if you want to go synchronous or asynchronous, you can specify the time, the location, longitude and latitude of the epicenter, the depth.
Carlos, I have another question.
Yeah.
This of asynchronous and asynchronous, what does this mean?
It means that you can set different times for the rupture of each fault. Okay, if you consider, for example, 10 faults, you can specify that the first fault rupture is in time 0.
Okay.
The second one is in time after 5 seconds, and the third one is after 10 seconds. So you can do a kind of dynamic rupture of all these faults that you are considering in these lines. Okay.
Okay.
You can specify the moment of the rupture of each fault. Okay.
Or
And
it's like you have a fault defined by different 2, 3, or very many segments. Okay, with the Okada parameters. So that's a nice feature of the code.
Yeah, the same for segments or the same for triangular Okada. Okay, if you go down to the option 3, you see here that for every fault, you can also specify the time of the moment of the rupture of this triangular fault. You specify the vertices of the triangle, the rake and the slip, but you can also specify the different moments for the rupture of these the different faults. Okay, so these all these things are a key feature for Tsunami-HySEA, because you can do a kind of dynamic rupture of the event you want to simulate. Okay, and what to say more? Okay, the difference between the seafloor deformation from file and the seafloor dynamic deformation from file. Well, you might be wondering, what is the difference between the option 5 and option 6? Well, in both cases, you provide the accumulated deformation. Okay, if you want to provide a seafloor deformation from file, you include a file. Let me go down to the option 5. Option 5 and 6. Okay, could be similar, but there are a bit difference between both. Okay, so if you choose option 5, you need to provide if you want to apply the Cayura filter and so on, and then you can provide the number of faults you want to simulate, and for every fault, you need to provide the file with the accumulated deformation, but also you can use time specification for this accumulated deformation file. Okay, so, and if you observe, the option 6 is similar, but here you just provide one GRD file, number of faults. It should be one, means that you only provide one GRD file, and this file is, in some sense, let's say that is kind of 3D netcdf file, because it contains all the formation and their respective times. And Tsunami-HySEA not only applies each deformation from the file at the appropriate time, but also interpolates the dynamic deformation in space, but also in time, applying its deformation at each time step through the simulation. This is the main difference between the option 6, because it interpolates the dynamic deformation in space and time, and the option 5, you provide a netcdf file for each deformation you want to apply, and Tsunami-HySEA applies them only at the specified time instance. Okay, so this is more or less the main difference between choose 5 or choose 6. Okay, and after that also you choose a Gaussian initial deformation by providing the longitude center, the latitude center, and the height and sigma in kilometers for this representation of a Gaussian as initial deformation. Okay. After that, after choosing the different initialization of a state that we can provide, well, let me go down. After that, or better if we move to the slides, it should be better. Let me again share the slides. After specifying the different property or coefficient to put under the initial condition, we need to specify a prefix, a file prefix, in order to name the output netcdf, and align. This is important because after specify the prefix, the netcdf file prefix for the output, we need to provide a line specifying the variables to be stored. Okay, 1 to save, 0 do not save, and the different variables we could store are eta, maximum eta, the maximum height, the height, maximum height, velocities, maximum velocities, the modulo of the velocity, the maximum modulus of velocity, maximum modulus of mass flow, momentum flux, the maximum momentum flux, and the arrival time. If you count them, there are 10 different variables to save for our simulation. Okay, so after put here the output file prefix, we specify which one of these variables we want to save. Okay, with 1 to save, 0 do not save. Okay.
And there is two kind of variable, because we have the variables that are 2D, let's say the maximum of any quantity, and other that are time dependent. So if we store them, we will have a 2D in space, and also the time variable, and we must. So two different.
Yeah, we can, for example, this one, the maximum modulus of velocity, sorry, is just at 1D, let's say, or 2D, but the eta we can store every 60 seconds, and to know the behavior of the simulation of this variable along the time, okay? After specifying the variables to store, we can use more than one level, okay? We will see later in the case of nested meshes that we can also use different level of resolution. And for each level, we need to specify the refinement ratio in order to nest with the finer resolution grid, the number of submeshes, and for each submesh, we need to specify the same, the bathymetry file, the path for the bathymetry file. Then if we have to use the initial condition number 0, we need to provide also the initial state file for this submesh, and then also specify the name of the file for the output, a line specifying which variable we want to save for this level, okay, for each submesh. And after do that for each level, okay, we also provide other variables, such as the border condition for the boundaries, 1 for open, -1 for wall, upper, lower, left, and right border condition. Then we put here the simulation time in seconds. We want to simulate 1 hour, we put 3,600 seconds. And also the frequency of saving a netcdf file, what Jorge commented earlier. if we put here a simulation time, we put here the frequency in order to save every, let's say, 1 minute of simulation in order to see the behavior of the simulation, okay? Not only at the end, but also in every 60 seconds, for example, 30 or whatever, okay? It would be nice to store this time step in order to, let's say, to create an animation and to see the behavior of all the simulation, okay? The next line is read points from file. It means that if we, it's an option to read point from file to store time series, okay? By using, for example, forecast point, virtual or real gauges or whatever, we need to specify the file with the points and also the frequency of the saving time for this time series, okay?
Okay. Carlos, before you go to the technical
Yep.
part, that is
Yep.
CFL, can you go to the previous slide?
Yep.
Just a little explanation in what is the levels. The levels are the domain with different resolution we are going to use. So for the previous trainings course that we did, we use just one level. That means we only do propagation. We only have a domain that has a given resolution of 100 meter, 1 kilometer, or whatever. And the different levels means increase resolution to do this nesting grid. We can have 2, 3, 4, and every time we go to move to a next level, we have a increased resolution. So we are going to do, probably we will see a picture from Carlos very soon. And the important thing is that each level, because there are two concepts here, each level may have different submeshes. So we may have within a level 2, 3, 4 meshes in that level. So we will see in a picture, but just make clear what means this level here. So they are resolution and pieces, let's say, of mesh with a given resolution that will help us to get to the higher resolution at the end. Okay. Thank you. Sorry.
Yeah. Thank you for this. Yes, I will illustrate this in a couple of slides later. Okay. And as it was the technical part, I'm not going into the details of the different parameters. I mean, the rest of the parameters has to be with the scheme, the CFL condition for the stability. The epsilon H is kind of the threshold for the wet dry cell consideration. Also, the threshold for this switch of a scheme. I mean, we need to specify the meter for the bathymetry depth in order to switch between the propagation part of the scheme and the inundation part of the scheme. And also the stability coefficient. We need to specify for each level of resolution this stability coefficient. I mean, we won't delve into the details of the intrinsic parameters of the model, and in these examples, we will use the standards, let's say, so a better understanding of the numerical model will give us the opportunity to understand the behavior if we modify a bit these values. Okay, Jorge, I don't know if you want to add something in this technical part.
No, I think that we can leave it like that. Just to say that the CFL, the standard one is 0.5, and if we increase the scheme, normally could be unstable and stable, but may not. At the same time, the larger, the faster you move in time, so has the advantage and the disadvantage. But it's something that you must gain with the experience.
Okay. Thanks. What more? Well, the friction type, we can indicate here if we want to work with fixed or variable friction. If we choose fixed friction, we just put here the water bottom friction, the Manning coefficient. But if we use one we specify the file with water bottom friction for the corset level, the level 0. But also if we want to apply different friction terms for each submesh, for each level and each submesh, we can also provide these meshes with the with the variable coefficient for the friction. Okay, the latest version of Tsunami-HySEA includes, among other improvements, the incorporation of the variable friction. This feature involves, assigning different water bottom friction coefficient to each cell, allowing the examination, the validation, know the fluid behavior based, for example, on land use. Okay. This version is not yet open, let's say, to the public because it's just testing now and validating. It has been recently presented in EGU, for example. I conducted a study on flooding with a resolution of 7.5 meters along the entire coast of Puerto Rico, analyzing the influence of the land use on tsunami flooding for many sources, 30 sources. But well, we can see that this advancement will soon available. So you can, you will be able to work with this friction, variable friction, let's say, improvement of the Tsunami-HySEA code. Okay, but in this course, in this example, we will use just fixed friction, Manning coefficient fixed for all the levels or all the grids. Okay. What more? After that, you can just put the other standard numbers, such as the maximum allowed velocity for the water, the typical length, the typical depth, and if you are going to store arrival time, you can also specify the threshold for considering arrival time in meters. So if the water height is more than 10 centimeters, I consider as arrival time. So you can, if you are put previous here a number 1 to consider to store arrival time, then you can specify here the threshold for the arrival time. Okay, so this is more or less how you can fill the parameter file. We will see in an example in a while. And this is about the parameter file, and then about the management of GPUs. Okay, if you remember, the third main ingredient was the management of the GPUs. This is very easy because you just need to run the command get load balancing, followed by the part file, and indicating how you want to divide your computational domain, indicated the number of processes in X, number of processes in Y. So, for example, the load balancing program should be executed to create this decomposition of the domain. For example, if you have 4 GPUs and you want to divide your computational domain in these 4 GPUs, you just put get load balancing followed by the part file, and then you put 1 by 4 or 2 by 2 in order to have or assign different part of your computational domain into each GPUs that are available. Okay, so it is important to run this load balancing program to generate all the necessary for the load balancing for your problem. Okay, so and also if you only have one GPU, you put 1 by 1 here, and all the computational domain is assigning to one GPU. Okay, but it is important to consider if you have more than one GPU, you can divide your domain into them. Okay, we will see later in the examples. So After that, we just talk about the input files.
May I ask a question
Yeah.
about this? I have one version that is the 4.0.0, I think, that doesn't require this step. And I'm a bit confused on how it deals with it, because I was talking to Mark and he said, oh, you don't need to run the get load balancing with this version. So is that just specific for that version? And I'm not sure how. Yeah.
I don't know how Mark did.
Yeah, I'm aware of that, but I forgot the idea. But one thing is that this 1.1.4 or 4.1 or 2.2 may be important, because you don't do the decomposition in any way, let's say. So depending on where you have most of the water, okay, in your domain, you may want to choose one or another. That is difficult to explain by words. Very simple with a picture, and but it's true that it's not necessary in this version. But in that case, you do the composition by default, or probably it's automatized. I don't remember.
I don't remember.
Because I tried to run it, like I didn't get the srclb file or folder, so I just used the previous one. But then I tried to run it and it just gave me some error that the friction should be some 0 or something. And then Mark said, oh, but you don't need to run the get load balancing. So I was just wondering, okay, but maybe it's just that specific version.
But don't worry, we will come to you answering in detail. Okay.
Thank you.
Okay, and
we must say that she has is a advanced user and also having access to the very latest version of the code. So are not version that are not usually they're not available for all user. That is the case, the one Carlos is explaining.
Yeah, sorry.
Okay, so once we have all the main ingredients, we can just run Tsunami-HySEA. So these slides presents an example of how to execute Tsunami-HySEA in a cluster environment using bash script to configure the simulation. So we need a bash script header and just the configuration in order to establish the connection with the characteristics with the cluster, just the job name, partition, the output folder, the number of nodes, the resources. Well, we are going to use GPUs, the time limit, etc. And then after that, after this header, we just need to run the executable of Tsunami-HySEA, MPI run, the path to Tsunami-HySEA, and the path to the par file. Okay, so if we put this in a bash script in order to work in a queue, we just run this script by using, for example, sbatch in the cluster. We will see in a while. Okay, so that's easy. Once we have the main ingredients, we just configure this script and run the Tsunami-HySEA. So what about the outputs? Well, the outputs, after the simulation ends, we will obtain these netcdf output files. Netcdf, it's Network Common Data Form. It's a file format for storing, the multidimensional scientific data, such as water height, velocity, momentum, temperature, humidity, pressure, etc., or related, in our case, or related with the tsunami outputs, okay? And as you probably know, netcdf formats is extensive use in scientific simulation because it is, self-described in nature, is closed platform, efficient storage, it's flexible, it supports chunk compression, integration with many visualization tools. So this feature make it a robust choice for storing and analyzing simulation outputs. And also, we will use this library, netcdf operator, NCO, which provide a suite of command line tools for manipulating and analyzing and post-process net-CDF file. Okay. So let's go to the matter now with the examples. Okay, we are going to start with propagation examples, and the idea is try to reproduce an event here in the Mediterranean, this part of the Mediterranean, very easy with low resolution. In this case, we are going to perform a simulation with a computational domain of one level and one arc-mean resolution grid. Very, very easy. So we need to get the ingredients. The first one is to create the bathymetry. We are going to create a GRD topobathymetry with the data of this region. Then the second step is create the part file for the simulation. The third step is to perform or to run the load balancing for our computational domain, and at the end configure the bash script to launch and run the Tsunami-HySEA for our case. Okay, so let's work on the fly. Let's go back to the Thika cluster and start with this example. Okay, I'm going to create all the things from the scratch, starting for the topobathymetry and all the things that we need. Okay, so let me move to the project, and here I have for the name ChEESE training. I'm going to put here, and I have here a directory about examples, but I'm going to create a new folder called, for example, propagation. Okay, so I'm going to work here, propagation. Okay, before nothing, we need to create our computational domain, our topobathymetric data. So the idea is try to download. Let me put here more or less an overview of what we are going to do now. So as I mentioned before, we need to create the topobathymetry as our first step. So to create our bathymetry, we can just go to a public service of data, topobathymetry data, like this one, etopo. Let me go to the viewer, to the grid extract, and here just move to our area of interest, in this case, and then we select our data, for example, this one, 1 minute, 60 arc seconds, okay? And we can just select the rectangular of our region of interest, this one, for example, okay? Small one, and then we can just download our data. Okay, this is a TIFF, GeoTIFF. Okay, I'm going to let me open and move here. I think it's in files. This is the TIFF I've just I just a while before the course, but it's more or less the same domain I have here is in TIFF format. Okay, so the first thing that we need to do is, let me back to the Python, not to the Jupyter notebook. The first thing is to convert from TIFF to our necessary format, that is GRD, the net-CDF. Okay, so we are going to use this command, that is the GDAL library. So if we have here, let me transfer my data to the cluster, that is files, etopo1 bathymetry.tiff. And here I move to the, sorry, software, no, the ChEESE training, propagation, and here I'm going to make dir bathymetries, okay, bathymetries. And here I'm going to upload my geotiff file. Okay. And here in the Fika-Machi, I'm going to load also module load the necessary library like GDAL, and I will use later also module load NCO, the two libraries in order to work with raster and to geotiff data. Okay, so after loading these two modules, we are now ready to translate our TIFF raster into GRD format. Okay, so we just put here GDAL translate. The output file should be netcdf. The format should be format equals to netcdf4. The input is a topo1 bathymetry.tiff, and the output should be a topo1 bathymetry.grd. Okay, so it's so easy. After that, we just have our GRD format bathymetry from this original data that was in TIFF format. Okay, and here, as you can read here, then we rename the band1 variable to set in the GRD file. Because if we use, for example, the netcdf info in order to know if all our variables are okay, we can observe here that we have the longitude in double precision, latitude in double precision, and not set, but band 1 in single precision. But we need to rename this variable into set by using, in this case, a tool from NCO, that is NC rename variable band1. I'm going to rename as set, and we put here the GRD file. Then if we just run this, if we enter again in the information of this GRD, we can observe here that we have our set variable named as set instead of band1. Okay, so just we have just our TIFF original raster converts into netcdf4 into GRD format. Okay, so our first ingredient is ready. We have just the bathymetry file. So let's continue with the second step. We need to create the par file, for this this experiment, for this event. We are going to consider, for example, an event like the 2003, the Algerian event. And here I put here the Okada parameters. Okay, so the other thing that we need to do now is to move and to create. Example, I'm going to name par file, or I don't know if I put here par file prof.txt. Okay, and we need to fill this parameter. Okay, so the idea here is to know which what to put in each line of this parameter. Okay, so how we can access to this information? Well, as I said before, we can just run the software HySEA version 4.3.0 bin, okay, Tsunami-HySEA. If we just run Tsunami-HySEA with no arguments, we are here the different lines in order to create our par file. Okay, so let me open here a new cell in order to put here what we are going to put in our parameter file. Okay, so the first thing is to name the experiment. I'm going to put here propagation med from Mediterranean. Okay, propagation. Okay. First line, this is the bathymetry name. Second line is the bathymetry path, okay? That is in the folder bathymetries, and its name, if I remember well, a topo one bathymetry.grd. Okay, the third, sorry. This is not marked down. This would be okay. The third line, we need to specify the initialization of state. In this case, we are going to apply for one segment of Okada parameters. So we just put here the number 1 corresponding here to Okada, standard Okada, okay? Next line, if we choose this one option, just go to down here and we need to specify of these parameters. The first thing, if we are going to apply Cayura filter, in this case, we are going to put here 0. We don't want to apply Cayura filter. Then the number of faults that we are going to simulate, in this case, 1 fault, this one, okay? We put here 1. Here, comments, apply Cayura filter, no, then number of faults. Then for every fault, we need to specify all these parameters that are here above. So we put here 0.0, 3.65, 36, the location is 3383, 3683, longitude, latitude, depth in kilometers, 10, length of the fold, 65, width, 17, 54, the strike, 47, 86, and the sleep, 4.7 meters. Okay, these are the parameters. Here, Canada. Next line, move down because these are the other options from here. Next CDF file, we are going to save.
Here is, for example, Carlos, when we have more than one fault, one segment for the final, where we can have different times for the rupture of the different segments, and we need to include all the segments.
Yeah, or all of them at the same time. We can just put
all them at the same time, of course. Yeah.
Simultaneously, okay. If we put here number for those, we need to add another line, okay. Different parameters and even different times, okay. So in this case, we are going just to put one fault, but as Jorge said, we can just put several and different time rupture for every fault, okay. So following this, we need to specify the let me go back here. If we want to use Okada computation window, in this case, we are going to put here 0. No Okada computation window. Okay. And just because if we put 0, we don't need to put more. Okay, so next line should be the next.
And this Okada computation window is for what?
Is to restrict the Okada computation to a radius. Okay, so if you want to apply only the Okada deformation applied to the just a radius. Sorry.
I think it's in a square, no, or a rectangular. How it is?
I think is a circle
a
around
radius.
the
Yeah.
center, okay?
Okay.
So if you put here 1, you need to specify the radius of the area in which you want to apply the computation of the Okada, okay?
Okay. Not to apply, not to do the computation in the whole domain because it's
Yes.
not necessary. Okay.
Yeah. So after that, we move down to specify the netCDF prefix. So we put here that our output is gonna store in, for example, in the folder simulations with the prefix or this event is Algerian 2003, for example. So the output netCDF file should be Algerian 2003.nc from netCDF, okay? So this is the netCDF file prefix, and then we need to specify a line specifying the following variables in order to store or not to store, okay? So these are the variables, okay? So I'm going to save eta, for example, maximum eta. I don't want to know about the velocities, so I put 0. I don't want to know about the maximum velocities, 0, 0. For example, in order to just save the eta, maximum eta, and at the end, for example, the arrival time. So I want also to only to store eta, maximum eta, and the arrival times. Okay. If we want to also store the maximum momentum flags, we put here a 1. If not, we put a 0. Okay. So as you can see here, 3, 6, 9, 10 values for each of these 10 variables to store. Okay. Then, in this case, I wanted to perform propagation simulations. So I want only one level of resolution. I put here 1. So I don't want to fill this. And then I go to this line in order to put, so let me comment this line. Let's see the prefix. Variables, save number of levels, and then the border condition, open, 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 open. Border conditions, and then the simulation time. Okay, this would be the simulation time.
This boundary condition, this open boundary condition, means that when we have coast, it's coast, and you have inundation, of course. But when you have open ocean, it's an open ocean. So it's the normal one when you're doing simulation in let's say in real problems, to have one everywhere, because means that the ocean is open where you cut in the middle of the ocean. And when you have coast, you don't use that boundary condition. You have your coast that is there. So it's the normal one.
Maybe if you are working on a laboratory experiment or this kind of thing, you can just put a wall in your computation domain. But usually we use, in real case, we use open border. Okay. Okay, so continue with the simulation time. You can just put here, I don't know, 2 hours. 2-hour simulation, for example, and the frequency of saving. Yeah, just put here the simulation time. We need to specify if we want the frequency of time, the saving time. We can just put, in order to see the behavior of the whole simulation, 60 seconds. Okay, so every minute we get this kind of a snapshot of all our variables in depending on time. And in this first example, this line should be would be 0 in this case. you don't want to store anything about time series. So we put here 0. And then we put here the standard values, 0.5 for the CFL. The epsilon h, we can just put, I don't know, 0.60. And this is the epsilon h.
Okay, so here we have a question from Felipe in the chat. The first one regarding the CFL, I've already answered in the chat. I just hope that I did not privately. I don't know. In case I did, I will share now to everyone about the CFL. That was enough for Felipe. And the second question was regarding the epsilon h. So we have 2 epsilon. The first one Carlos mentioned before is this one, that is the epsilon you use to say that you have a wet or dry cell. So it's a kind of technical one. So this epsilon is small, and it means that we have a certain water, a certain level of water in a cell. You consider it dry, wet. Okay.
Well, yeah.
At the end of the part file, there's another epsilon that at the beginning was used as this same one, but we're given many problems because it's used to decide when you say that the wave has arrived in order to compute the arrival times. So we have 2 epsilon h. This one is for saying when you have a dry, a still dry, or already wet cell in your simulation.
Yeah, yes. Okay.
Thank you, Jorge.
You're welcome, Felipe.
This next, in our case, we just put here 20 meters in order to consider the switch value in order to switch from the propagation scheme to the inundation scheme. In our case, we are going to use only propagation because of the low resolution of our computational domain. And the stability coefficient should usually use 0.2. And then, well, let me comment this. This is the threshold for the 2S or WAF scheme. And this is the stability coefficient. Okay. And then align specifying the friction. In our case, we are going to consider just fixed friction. Our Manning coefficient should be 0.03, for example. And this is the Manning coefficient. And at the end, the maximum allowed velocity of the water, we can just put 100, I don't know. Typical length, 10 kilometers, typical width, 100 kilometers. And what Jorge mentioned earlier is that we can consider different epsilon in order to consider that the wave is arrived, yes or no, arrived in time. So we can just put here, if we consider more than 10 centimeters, the wave is arrived. Okay, this is the
this L and this H are the parameters used to adimensionalization. Okay, so usually for the length we think of 100 kilometers if you're in, I don't know, the Mediterranean, so in meters, of course, and for the H it's the order of 1 kilometer, so more or less is the width, the length, that the height that the depth that we use as reference. Okay.
Is it something you would change if you go
No,
to the
not
Pacific,
really.
for example,
I mean,
or
probably you could change in the Pacific and you have one more zero in the typical length. But, okay. So yeah.
Okay, so we are.
But of course, it's there because when you move to a experiment in the laboratory, that might be drastically change.
right.
So if for small changes is not dramatically changes, is as I said, is for adimensionalizing adimensionalize the results, the numbers. And also, I have the answer to your question, Valentina, because I think that you're using the Monte Carlo version, isn't it?
Yes.
So Monte Carlo version, who does Monte Carlo version?
Right.
Use a single GPU for the
Right.
idea is to
For
do
each
very many
simulation.
simulations using a single GPU, so you don't have to do the load balancing.
The load balance. Yeah, okay,
Yeah.
that makes sense.
That's
Thank
the
you.
reason. Yeah.
I was imagining that it
thanks.
was the Monte Carlo version that only needs one GPU per job. Okay.
Yeah.
So,
You may
Thank you.
use one very many 64, but you're using so no need to do balancing.
Yeah. Thanks.
okay, so this is the content of our parameter files. So let me go back to the Theta cluster. Let me edit the part file of propagation and just copy these lines into the file for our simulation. Okay, so the idea is that once we have our parameter files, once we have our bathymetry, the third ingredient was do the load balancing. Okay, so we move to our executable that is in software HySEA 4.3.0 being LB, get load balancing, followed by the part file, and followed by, in our case, we are going to use only one GPU. So we put here 1 by 1. And if everything works, it's okay. Here we just have the information of our problem. Okay, this is the information of our problem. It's a very, very small domain with just 400,000 of cells. Okay, and as you can see here, we are just created this bin file that is our name. Okay, here you have the bathymetry name or the event or the experiment name, followed by the number of levels and the number of GPUs we are going to use. Okay, so what are the content of our folder? We have the part file, we have also the bathymetries. We need to create, because we put here the folders for the output, we need to create the simulation folders and make dir simulations in order to store the netcdf, the output. And just we need to create the job, job configuration, the bash script, in order to launch our simulation in the CoE system. Okay, so I'm going to just create this file job using one GPU.sh. Okay, I'm going to edit. And I'm going to just copy and paste this. I'm going to just put here as, and you can see here, sorry. Again. Okay, so the job name should be my name, prop, or let me put here, I don't know, Algerian. GPU partition, we are going to store the output of the Tsunami-HySEA execution, not the output of the simulation, but the output of the Tsunami-HySEA execution in this folder. So we need to create this folder. We are going to use only one node, only one GPU. The time limit very, very small, just 10 minutes in order to complete the simulation. And we need to, I'm going to change this, because we have now in this folder projects, ChEESE training, propagation, and we just invocate the command mpi run, followed by the executable of Tsunami-HySEA, and followed by the path to the part file that we have just created. Okay, so I'm going to save here, and I'm going to create also the make the out folder in order to save the output of the Tsunami-HySEA execution. And we have already all the ingredients, so we just need to execute the bash script in order to launch our simulation. Cross finger, batch job. Okay, as you can see here, I've just submit this job. This job has this name, and if I skew my user, no, sorry. Maybe something happened. Let me cancel the job. No, it's okay. It's okay. It's just end after 5.5 seconds. Okay, so we have just simulate 2 hours of simulation in just 5.5 seconds. So maybe if we move to the simulation folder, simulations, here you just have the result, the net CDF for this experiment, Algerian 2003.nc. Okay, so in just 5 seconds we have simulated 2 hours, if I remember well. Yes, 2 hours of simulation. Okay, so one thing that we can do directly in our cluster is to have visualize our simulation by using ncview command followed by the netcdf. Let's open this, and as you can see here, we need have this interface in which we can choose our variable. We have the original bathymetry, the deformed bathymetry caused by the fault, the Okada standard Okada fault, the maximum height, the arrival time, and also the eta. That these are the 3 variables that we put in order to store. Okay, so if we put here, just click here, we can see our computational domain. Okay, let me share the color map in order to see better the maybe this one. That is okay. I'm going to put the minimum in -2 and maximum 2. And here you can see the initial condition, okay, the first configuration of the initial condition. And if you put here in forward reproduction, you can see the behavior of the simulation in time, okay? Because we have stored every 60 seconds, so we have 120 snapshots of the simulation for the eta variable, okay, for this. I put it again. If we put here, for example, from -1 to 1, here you have the behavior of the simulation, okay? So as you can see, it's very easy. We only need the topobathymetric data, a small domain or big domain or whatever, and just configure the parameter file, put all the lines in the correct position, and just configure the job and run the simulation. Okay, so let me back to the slides and stop here. Okay. Let's back to the slides. And the post-processing, as I mentioned before, you can just open the NC viewer in order to just have an idea of how your simulation has gone. And also you can try to create some plots like this one by using a Python script. So if you are familiar with Python, you just need to load some libraries, some like netcdf or matplotlib, numpy, cartopy in order to plot your maps. And then once you have read the netcdf file, you extract your longitude variable, latitude variable, and the max height as variable, and just, well, I can provide you this script in order you to modify if you want, and then try to create this kind of plots in order to represent your results. Okay, so this first example is very easy, and one of the things that we can do is add, for example, as an exercise, add forecast point in order to analyze the behavior of the water height along this forecast point. So how we can do that? I have selected some of them, and the idea is that if we have the location of this virtual or real voice, we need to create this file. Starting, the first line is the number of points, the point of interest, and then the location, the longitude and latitude of each for each of these points. And the only thing that we need to do is to modify our parameter file. So let me upload this file into our folder there. Here I can just upload this into our folder in the Zika machine, and then let me show you this file. This is the file with the point of interest, the location of the point of interest. So you can see here that is the first line is the number of points, and then the location and the longitude and latitude of each one. Okay, so as I said, we only need to modify our par file. So let me enter again to edit the par file. And here, if you remember, we put here a 0 because this is the read file for time series. Okay, so in this case, I'm going to put here 1. And then, if you remember, we need to provide the file that is fcp underscore med.txt, and then the frequency for saving time series. Okay, so I put here, for example, every 30 seconds. Okay, so I have just changed this line and this line. Okay, I'm going to save again, and the rest of the files are the same. I'm just need to again execute by using sorry, batch job 1gpu.sh. Okay, this is the job, and it's just finished. If you can see here, if I put the cut out and the job ending in 6, sorry, netcdf friction file have shown that. Okay,
I
so
think
that means
because I think
yeah,
what you changed, it was like
the
friction
wrong
type.
line. Okay, so
Yeah.
so
I wasn't entirely sure.
uh,
But I think before
this
it was
one.
friction.
Yeah.
Yeah.
So here, let me put again here a 0 because this is the friction. Yes, this is the friction. Yes. Friction is fixed we use, and this one, if I remember well, is the here the line that we need to change. This is the read. Sorry for the error. Read file for time series. We have with fcps met.txt, and then every saving time every 30 seconds. I think it's okay now. Okay.
Here,
Save.
a small comment that when you want to save the 2D field, 1 minute is too much in general, and when saving the time series, 1 minute is like the minimum, let's say, because you need to not to lose this time series.
Yeah.
Okay, so yeah.
Okay, so I run again the bash script in order to run the simulation, and 5 seconds, 7 seconds, 8 seconds, that's just end. And now, if you go to the simulation folder, you will see two netcdf files, one for the simulation and the other one ending in _ts from time series .nc. Okay, so this file store the simulation time series for our points. If you enter about the info for this file at gbn.ts.nc, okay, here you can observe that we have several variables, but the one that are in is our interest is this one, because it depends on time and the grid endpoints that are the different points of interest that we are interested in. Okay, so one thing that you can do is, let me go back to the slides again, is use a script, Python script, in order to plot the time series here, for example, these points that are here. Okay, so you just read the time values, you read the eta variable that depending on the time and the different points, okay, and just plot the time series. Okay, so you just is just read the netcdf file and work with the variables inside. Okay, so our first easy example of propagation in a small domain, even by storing time series, is completed. Okay, so you are just ready to do by your own. So if you want an exercise here, I provide you an example of an event in the Pacific, in the Colombian Trench, with the Okada parameters. So if you try to do the same as I did before, you should be able to obtain the result like this for the maximum height. And also if you want to analyze the time series for this dart voice, I will provide you the data in order to reproduce this exercise. Okay, I don't know the time.
Okay, Carlos, I think a small break that was supposed to be 10 minutes ago
Okay.
for a small rest that we can do, I don't know, 5-10 minutes. I don't know.
Yeah,
what do you feel? But you are on the command. What do you
yeah,
say?
15 minutes is okay for me in order
Okay, we
to
can perhaps we can go back at 16:50 in 10 minutes.
yeah,
Yeah.
for me it's okay.
Okay.
Yeah, for me it's okay.
10 minutes to 5
10 minutes to
o'clock.
10
yeah.
minutes to 5.
10
Yep.
to 5, yeah.
Okay.
And
Then I think there are some questions, but maybe after we come back, we check the chat and answer the
Okay.
questions. Okay.
okay, yeah, I tried. There is just one that I left.
Okay.
The rest
Perfect.
I was answering.
Great. Okay. I'll see you all in 10 minutes.
Okay,
Okay.
see you in 10
Thank
minutes.
you.
Bye-bye.
So
Let's
let's go for
continue.
the final part. Yeah, please.
Okay, about the last question in the chat, just to say that in the job, the bash script that launched the job to the queue, is just well, with the sbatch command you specify some characteristics for the understanding of the CEECA machine in this case, or in your HPC machine, the job name, the partition, the output, the nodes, the resources, if you are going to use GPUs, the time limit. Also, you can specify the memory and that. And the last two commands are, this one is to change the directory to the folder in which you are your data. And the last one is the important one, that is the MPI run, followed by the path to the executable of Tsunami-HySEA, and followed by the par file, the parameter file. Okay, so the important one is this, but the other is just to change the directory to the correct folder, to the correct directory. Okay. Okay, so let's continue with the. Let me back to the slides. So we have just worked on this thing, the exercise proposed, and I wanted also to talk about the different initial conditions that we can just put in our parameter file. For example, if we have just talked about them, but in order to illustrate the thing, here you can see the initial deformation for the sea surface, just providing another GRD file that just must be included, or have the same size, but you can also use a small one that is nested with respect your computational domain. We have just talked about the seafloor deformation. You can provide a GRD file with the accumulated deformation, static or dynamic deformation, multiple Okada, only one segment Okada, standard Okada, Gaussian initial condition, and here I wanted to illustrate how dynamic multi-Okada works, because in each time you can represent the rupture of different faults in different time steps. Okay, so you can not only work with a standard Okada, but you can use different initial conditions. Okay, so let's now jump to the difficult part of this course, the hottest spot here, let's say. That is the nested meshes algorithm in order to achieve high resolution inundation for tsunami simulation. Okay, so the idea behind nested meshes is that let's say we typically have low resolution data over large domain. For example, here we have the Gulf of Cadiz, and as we can approach our area of interest, we will have better resolution data until we reach to an optimal resolution in order to evaluate the inundation, the flooding. Okay, so well, as I write here, it's important. Well, we start from a mesh of a certain resolution, and then we can build a set of nested meshes with respect to the previous one, let's say, from a refinement ratio. Okay, so it's important. I can show you a graph in the next slide to show you how you need to distribute the cells of each level when you are nesting your grids. Okay, so we start, for example.
So, for example, if you go to the previous slide, Carlos, here, for example, we have what we were saying before. We have 4 levels of refinement, 4 levels with different resolutions. You see that the black one that is marked, you see there in black, is 320 20 meters resolution. Yeah. Then the ratio to go to the next one, that the blue is 2. That means that we divide by 2 the size, and we increase the resolution. And the next one, this refinement ratio is 4. We go in the green one to 40 meters. And finally, we are going to do the inundation at the coast as a resolution of 5 meters, because finally there's a a ratio of refinement of 8 at very land. So we get to the coast with a pixel of 5 meters resolution for inundation. So these are the 4 levels in this case that we were mentioning before. Okay,
Yeah,
thank you,
we
Carlos.
use here 4 levels in order to pass from 320 meters up to 5 meters of resolution per pixel in the small one in red domain. Okay. So I'm trying to illustrate the process. So we start with our level 0 grid, our, let's say, ambient grid, and we will nest the next level of resolution where each new point of the grid will be located at the center of the subcells resulting from this refinement ratio of the coarse grid. So we establish a refinement ratio. So first we define the ratio, and that should be must be power of 2 ratio. So we can just use 2, 4, 16, 64, etc. So must be a power of 2 refinement ratio. And then after establish the refinement ratio, we create a new subgrid. So in these points, new points in blue, the points in the center of these cells in blue, we interpolate the finer data onto this grid. Okay, so to pass from level 0 to 1, we select a reduced area or reduced extension of our domain. We refine our cells. We obtain new points that are in the center in these subcells, and here we interpolate our finer data in order to have the better resolution data, but now nested on our previous level in this case. Okay, and so on. All the levels we are going to consider, always taking a refinement ratio as a power of 2. So we are able to select a small extension of our domain in which we have better resolution data. We refine our grid in order to obtain the points in the center of these subcells consequence of the refinement, and then we interpolate our data in order to have nested with our previous level, and then with the rest of the levels that we are going to consider. It is important to also to consider that there are certain, let's say, restriction on the boundaries of the grids, as so you can see here, the edges of the grids at a certain level cannot coincide with the edges of the previous level. Okay, so the points here in yellow, or the cells here in yellow, are not allowed because the edges of the extension of the domain coincide with the previous one. Okay, so these cells in yellow, or this one in yellow, are not allowed because the edges from one level to another are in the same place. Okay, so here, so to illustrate the example that we showed before, if we want to achieve, for example, in this case, a resolution of, let's say, 5 meters in a very specific population area in which we are interested in inundation, we can consider this set of nested grids. Okay, so starting from level 0, here I'm exaggerating the resolution, right? Okay, but we set our level 1 in blue. We refine this mesh. We interpolate the new data in this center of the intercells, consequence of the refinement. Then we set our level 2 here in green. We refine them and select our data here. We again determine our area of interest, now in red. we refine the same in the same manner. And even if we add another level of resolution, we need to refine and use the finest data, but that matches with the points consequence of this refinement. Okay, so the best thing is to see this in an example. Okay, and here I present you a script on how we can nest grids. Okay, you can build your own script, always following this instruction and consideration I mentioned earlier. And here I show you a script by using Python and this mentioned earlier GDAL library. Okay, so the idea is simple. I'm going to show you an example of how to nest two different grids. Okay, so the first thing is this kind of function. The thing that this function do is just a simple function that reprojects the fine grid, let's say the fine data, the fine grid image, raster, TIFF, or whatever, in order to match the coarse grid projection and resolution. Remember that we need to have the finite data in the points of these blue cells, in the center of these blue cells, in order to be nested with the previous level in black. Okay, so this function is in charge of that. Vale? Okay, so you can analyze deeper when you get the material, but the thing that this function do is just take data, usually finer and not aligned data, in order to match the master projection and resolution. Okay, so it's very easy. And the thing, the main part of the script is this one. Okay, here you define the input parameters, such as the file paths for the coarse grid and the fine grid raster. Here I'm going to work with TIFF, but as you saw before, then you can just convert into GRD when you have the nested TIFFs. And you define a ratio of refinement. So the idea is, first, you read the coarse grid in order to get or extract the spatial resolution, okay? And you crop this coarse grid to the extension of the fine grid, okay? So you have data, finer data, and you crop your coarse level, your cross grid in black, according to the extension of the fine grid. Okay, so you obtain the grid here, the extension of the grid here in blue. Okay, then you apply your refinement of ratio, whatever ratio, okay, and you obtain this blue grid with the refinement ratio that you have considered, dividing the resolution obtaining from the coarse grid by the ratio of refinement. So you has new resolution grid of X-res and Y-res, that is the division of initial resolution by the ratio of refinement, okay? And then once you have this, you have the finite data, original fine data, and your master file in which you need to reproject your fine data, okay? So with the function that is defined before here, with this function, you just reproject your fine data into the proper nest mesh with this refinement ratio, okay? So this output is just, in this case, the TIFF that you put here, the TIFF nested data, but with the values interpolated in the correct cells or points for the nested mesh. Okay, So you start from a coarse data, you have fine data that might be not aligned with your resolution of previous grid, but with this function you are able to reproject this data into this master file or match file in order to have both grids nested. Okay, after that you just convert from TIFF to GRD, the coarse one, the original one, the coarse, and also the fine one. Okay, so if you are going to use this script, you will obtain the TIFF, but also the GRD output of this one. Okay, so let me show you in an example. We are going to start from this with this example of Caribbean wave Lantex 2013 by using nested meshes. So here we have the parameters, cada parameters of one event located here, and our objective, our goal here is try to start from a low resolution in an ambient grid up to obtain to try to perform inundation results in a resolution in a small area of computational domain with 7.5 meter of resolution. I choose this one because it not take long and we can just do live in a while. Okay, so the idea here is start from an ambient grid here in black of nearly 2 kilometers of resolution, then apply a ratio of refinement of 4 to obtain this region in blue of 480 meters resolution, then apply new level of 8, ratio of resolution of 8 by obtaining 60 meters per pixel resolution in this green area, or the Puerto Rico island. And after that, just apply a new level by using a ratio of refinement of 8 in order to obtain 7.5 meter of resolution. Okay, this is because we have data here, very good data of this region, this harbor or whatever, this town here with a resolution of 7.5. So the idea is how we can achieve this high resolution for this area. Well, by using nested meshes in order to have a big ambient grid in which we put our initial event, the initial condition of our fault event, okay, but then try to go up to 7.5 meter resolution. Okay, so let's work on the fly. Let me back to the Thika, and I'm going to create a new folder named inundation. Okay, so the idea is, let me move to this thing. So the idea here is the same. We need to apply for well, to do the same. First step, create the bathymetry file. Okay, so I want to show you what are the data that I have here. I have 4 sets of data. I have data of 1,920 meters. I have also data of 240 meters. I have data of 30 meters. And this small area is called Ponce region or something like that. That is 7.5 meter of resolution. Okay. All of these things are TIFF. Okay. And this is the representation of this, more or less, this extension. Okay, but if you sorry, I need to switch again to this. Okay, so I have data here, data here, data here, and data here, but not with this resolution radio. Okay, so I have different pixel resolution here in order to create these nested meshes. Okay, so first of all, I'm going to upload this data here. I'm going to create a new folder named bathymetries, and then I will allocate here all these. Well, I'm going to work in local, so let me go back to that. Okay, so the idea here, I'm going to just run this script. It's the same that I put in the slides. So this is to run the function, and as you can see here, I have the course grid is. Let me delete this in order to show you all the process. Okay, so I need to specify here Lantex data. Okay, so I have to specify here the coarsest level, that is Lantex 2013 underscore 1920 meters dot TIFF. This is my course grid, okay? And I have better data resolution, that is this one, okay? This is Lantex 2013 240 meters dot TIFF, okay? And I want to create the first level of resolution that if you remember, I want to have the blue area not with 2040, but with 4080 meters. So I'm going to refine my original resolution, that is 1920 meters, by a ratio of 4. Okay, so in my script, I put here ratio of 4, and the output should be Lantex. I can put here Lantex 13 underscore L1, okay? Because I'm going to create the level 1 nested with the level 0, okay? We apply a ratio of refinement, and then just the rest of the script is okay. I'm going to run this, and as you can see here, create a new file, nesting grid, in this case, just a warning here, nested meshes created. And in this directory, you observe here, I have just created the Lantex L1 nested.tiff and the corresponding nested.grd. Okay, so this one, that is the original TIFF, I also convert it to GRD, and this one, level 1, is just nested with respect to the level 0. Okay, so easy. I'm going to change. Now I'm going to consider my course grid, the Lantex 13 nested.tiff, that is this one, because this one, L1, is just nested with respect to the level 0, okay? And I'm going to consider better new data, but better in resolution, that are the next one, that is in 30-meter resolution. So I have data with 30-meter resolution, but now I want a new grid, but with 60-meter resolution. So I want to apply a refinement ratio from the previous one, the level 1, to obtain 60-meter resolution. So I need to put here a ratio of 8 in order to obtain 60-meter resolution. So the only thing that I have to change here, I have to put here Lantex 2013 underscore 30 meters dot TIFF, and the results I wanted to store as L2. Okay, the script added after the underscore nested dot TIFF, but the original name is lantex13.l2.tip. Okay, but now I want 8 as the ratio refinement of the grid. Okay, so this is the course, my new course grid. This is the data. Might be no alignment with the grids, but what I'm going to obtain is is just aligned with the respect the previous one. Okay, so we have just done this, creating Unix file, nested grids, nested meshes created, done. Okay, as you can observe here in the directory, I have just the L2 nested grid, L2 nested.tif. Okay, and the next step is starting from this course grid in order to apply this new ratio of refinement and obtain this region in red with 7.5 meters resolution. Okay, so the only thing that I have to change here is I'm going to start from L2. Okay, the data that I have now, better data that I have now to interpolate is Ponce.Puerto Rico _75.chief. Okay, these are my better resolution data. I want to interpolate in a grid that is nest with respect to this one. I'm going to name L3. So I have L0, that is this one. This one is level 0. This one is level 1. This one is level 2. And I'm going to create now the last one. Also, we use a ratio of 8. And if we just run this, oh no, sorry, what happened? Maybe some of this, the n of meters here. Okay, so this is correct. This is now correct. The result is L3. Okay. Warning, blah, 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 raster created. Okay, and this one, this new raster, L3, is the last level. Okay, so now I'm going to move to the cluster to inundation bathymetries. I'm going to just move the level 0.grd, level 1, level 2, and level 3. Okay, I'm going to upload this. Okay, and now I have just the main ingredient, the topography data, and they are all nested with respect to the others. And the second step is to create the par file. Okay, so the par file is different with respect to the propagation one, because we need to put that we are going to consider more than one levels. Okay, so for example, the title could be Caribbean 4 level. Sorry. The path to the bathymetry, I think it's correct. The initialization type is 1 because we are going to run Okada fault, Okada parameters. We don't want to apply Cayura filter. The number of faults is 1. Here we put the Okada parameters. We don't want to restrict the Okada computation window. The output is gonna be for the level 0 Lantex simulation Lantex 13 underscore L0. These are the variables I want to store in this case: eta, maximum eta, and arrival time in this case. And this is the critical part, because we need to put here that we are going to use 4 levels. Okay, 4 levels. The ratio of refinement for level 0 to pass from 0 to 1, that is 4. Remember that in our case, we are going to pass from this resolution to this resolution by using a ratio of 4, okay? And then the number of submeshes, in this case, we are going to use only one, that is if you remember the blue one. So we need to put here the name of our level 1 nested grid corresponding to the next level, the level 1, and followed by the line corresponding to the netCDF prefix in order to save the output, and a line containing the variables to save. Same, I'm going to store the eta, the maximum, and the arrival time. So after putting here the bathymetry prefix and variables to save, because I have put here only one submesh, then we need to put the next level characteristics that are first the ratio of refinement, in this case 8, ratio of refinement. So, refinement, the number of submeshes, and also the path to the bathymetry and the simulation netCDF prefix, also the variables in order to save. And at the end, the last level, also the ratio here, the number of submesh, the path to the bathymetry, and the prefix for the netCDF and the variables, okay? And the rest of the parameters are more or less what we are just commenting in the propagation example. Boundary conditions, the simulation time. In order to be a bit short with the simulation, is I'm going to put just 1 hour, saving every minute. I don't want to read point for time series, and the rest of the parameters are more or less the same. Here, because we have 4 levels of resolution, I have to specify the stability coefficient, that is something technical in order to control the stability for the scheme for every level. So level 0, level 1, level 2, and level 3. The 4 level that we are going to consider. The friction time is fixed, and the rest are more or less the same. Okay, I'm going here to consider that the arrival time is if more than 5 centimeters. Okay, so you can just put this content as let me enter in the indentation. I'm going to create here I don't know, langtext 13 for level.txt. And here I'm going to copy this content that we just commented into this insert. Okay. So what ingredients we have? We need also the make dir simulations folder, make dir out folder, and in this case I need to first of all the load balancing is the third step, so we need to run software-HySEA.0 bin Tsunami-HySEA followed by the bin lb get load balancing followed by the par file, that is langtext for level.txt. I'm going to use only 1 GPU. Okay, so if everything works, here you have the description of your experiment, of your problem. Here you have the different levels, the simulation time, saving time every 60 seconds, and the number of volumes and the location, the extension of your 4 levels. Level 0, level 1, ratio of refinement 4, level 2, ratio of refinement 8, and level 3, ratio of refinement ratio 8. Okay? And all the computational domain is assigned to an unique process. Okay? So it creates this binary script. So what more do we need? Yes, the job configuration. So I'm going to create also job only one GPU .sh. And here I'm going to copy and paste more or less the same as the example before in propagation, because we need to specify here. I'm going to put, I don't know, Caribe, GPU, Puerto Rico job, nodes 1 GPU. We can put here 30 minutes. We consider that our experiment will take a long time, okay? And we move to our directory, which is training inundation, MPI run, followed by the executable of Tsunami-HySEA, and followed by the par file of this experiment. Okay, so I'm going to hide this, and I think we are ready to run this. Okay, so I'm going to put this batch job 1 GPU, and if everything works, start with the simulation. Okay, so if you move to the simulation directory, change directory simulations, you observe that you obtain one netcdf file for each level. Okay, so we put here in each level netcdf prefix. Okay, so for each level of resolution, we will have this variable. Okay, this examples takes a bit, not so long, but it's still running. It will take 10 minutes, if I remember well, or something like that. So I'm going to switch to the slides again in order to show you another example. Just maybe some of you know this example is to show you that you can use this kind of computational domain with, for example, in this case, we use one ambient grid here, and then 4 level of resolution, but each level including 2 submeshes. Okay, so for the level 0, we have just this ambient grid. And you can see the map of the eastern part of the Mediterranean. Okay, and then the level 1 correspond to this extension, but also this extension. Okay, so we have level 1 with 2 submeshes. Again, for the level 2, that is this one, but also this, but also this one mesh. Okay, so the level 2 has also 2 submeshes, and the level 3 correspond here and correspond to this area of, this is Catania and this is Syracuse in the eastern part of Sicily, and also the level 3 has 2 submeshes. Okay, all of this scene can be written in the part file. Okay, so the experiment that we will try to simulate is an hypothetical tsunami in the Eastern Mediterranean Sea. This is the characteristic, the location of the earthquake, the magnitude, the Okada parameters, and we are interested in obtaining high-resolution inundation maps with a target area combining different level of resolution, with the goal of obtaining inundation maps with 10 meters of resolution, starting from an ambient grid of 640 meters of resolution. We are going to use 4 levels with 4 as the refinement ratio. So we are going to pass from 640 to 160, then to 40, and then to 10 meters of resolution, okay? By using 4 levels in order to pass from 640 to 10 meters, okay? So here I can show you the par file in this case, and you can observe here the same thing, but here, for example, the name, the path to the ambient grid, the same thing. We are going to apply for our Okada, standard Okada. We don't want to apply Cayura filter. We are going to use only one fault. These are the Okada parameters for this fault. We don't want to apply or restrict the Okada computation in a window. This is the netCDF prefix for the output results. And if you observe here, we don't have any variables to save. We have 0, 0, 0, 0, 0. Okay, so for our level 0, we don't want to save anything for our we don't want to know about the propagation of our level 0. So we put all the variables 0. Then we put the number of levels, the number of resolution for the first level, the level 1, and then here I put here 2, because as if you remember, we have 2 submeshes of level 1. Okay, so we indicate here that we have 2 submeshes. So for each submesh, we need to provide the bathymetry path, the prefix, the variables to save. Here I put again 0, 0, 0, 0. And this for the first submesh, this is for the second submesh, and we don't want to store anything with respect to the level 1, okay? Then we put the refinement ratio for the level 2. Again, 2 submeshes, one for Catania with this data, one for Siracusa for this with this data. Again, 0, 0, 0. We don't want to say anything about the level 2. And the last, the level 3 with a refinement ratio of 4. Number of submeshes, again, we are going to use one mesh for the Catania region, one submesh for the Siracusa region, the prefix for the netCDF file, and here I'm interested in store the maximum height, okay? The maximum height only for the high resolution grid, okay? For the last level, for the level 3. So I want to store the maximum height for Catania and also for Siracusa, but only in the last level, okay? The boundary condition, I'm going to just simulate 4 hours simulation, okay? So these are 4 hours. I'm going to save just the final final state. I don't want to save every time step. Here, in this case, I is interested in store the time series for this data, okay? Every 30 seconds, okay? So I have here points of interest for forecast point or whatever. I want to store every 30 seconds, and the rest of the parameters are more or less the same. Stability coefficient for each level, the maximum allowed velocity, in this case 40. And if you observe here, I have no lines regarding the arrival time because I'm not interested in stored arrival time, so I don't need to put anything in the last line regarding the arrival time. Okay, so we just ready for run this thing, and one of the things that I want to show you is that how to post-processing, we can perform the processing of the results in case of high resolution inundation maps. In this case, the only thing that we have to take into account is how to create this variable that I name as inundation depth, because we have only the maximum height in all the domain and another variable that is the original bathy or the original or the deformed bathy, because we need to compute this in Spanish is calado, in English I think inundation depth is okay. So the flood depth by using these two lines, okay? So we consider where the bathymetry is positive. I mean, in the water, we consider a non-value, and we calculate the inundation depth by subtracting, in this case, the maximum height layer, in this case plus, because the original bathy is in this area is positive and here is negative, so we can put here a plus. But the idea is to get the maximum height minus the value of the elevation in this point. So that in this way we can obtain the inundation depth, the flood, only in the let's say in land, okay, not in water but in land, okay. So with this kind of Python script you can just plot this kind of graphs. And well, if you are depending on your familiarity with the visualization tools, Python ability and so on, you can create more sophisticated graphs. For example, here I include the wave amplitude in water, the inundation depth in land, and also plots the time series for two of this forecast point. Okay, so let me go back to our example. It's just finished, so I move to the results, and we can just use NCView in order to, for example, in this case, I stored the level 0 variables, and here I can just plot this event. Let me change the column map to jet, for example. It's okay, yes. And the range from -3 or -2 to -2 to sorry, to our area of interest is more or less here. This is 1 hour simulation, okay, but by using nested meshes. This is the ambient grid, so you can see the behavior of the tsunami in our level 0 computational domain. As you can just visualize the level 1, it's closer to our region of interest, that is here. So you can see the approximation of the first wave, how to reach this area of interest, that is the next level. Okay. Then I can show you also the level 2. Here you can give this bigger with this button here, and let me put over, for example, this jet. Will appear here in a while. No. Here. Okay. Yes, I only simulate 1 hour because of the time, but at the end you can also visualize the level 3, that is the high resolution, at 7.5 meters. That is here, and put a bit here, and visualize how the wave arrived to the coast, and you can observe also more or less the inundation. And if you want to plot the maximum height here, you observe here the maximum height in this level 3 computational domain corresponding to 7.5 meter resolution. Okay, so if you want to plot a graph like the previous in Catania, you just download your data, or you can so work directly in the cluster. But here I download the level 3.netcdf. Then I calculate the inundation depth variables. I apply the same script that I have shown before. And if it works, yes, here you can see the inundation depth, only plot in the land, okay, not in water. Here the inundation depth considering from dry to wet, okay. So it is the flood map for this for the region we are interested in, okay. So I don't know if there are any question on the chat or not, but let me say that that's all from my side for now. I hope I didn't go too fast with the explanation, nor too slow. And well, all as I said before, all this material, the presentation, the slides, and the files, and also the scripts that I have been shown will be included in the material, so you can practice and launch your tsunami simulation using Tsunami-HySEA. That was the goal, and I hope you have let's say found it useful. So thank you all. If you have any question, please contact
Carlos,
us.
we were discussing with Steven about the ratio of refinement in the chat. She was saying if 8 was too large, or if 16 or already too risky. I mean, we
The
didn't.
usual value is 4. If you need to increase your number of levels, it's better to consider 5 or 6 level of resolution, but using 4 as the refinement rate in order not to lose the data resolution. I think it's
there are several things that, as I was trying to answer in the chat, that is, one thing is where do you have the data? Which are the data at what resolution that you have? So that in some sense make your nested grid to be one or another. And the other thing is at the end the total size of the problem, because doing this kind of experiment you might end it with huge problems that if you save all the files, it's the huge size file. So you must take all that into account, and probably it's a good practice to move from one level to another in steps, and probably is the best. But it's something that we didn't do a formal study on the eventual sensibility to that. Well, I don't know if there is more question in the chat after that.
Let me
There's a question, please, where we can download the 3D file where you have the inundation in the present slide. Which one do you mean, Mohammed?
The one in the right side is just correspond to the I think that video promotional of the ChEESE project.
Yeah, we did. We have yeah.
And the last one is, why do you use the original bathymetry and not the format? Well, the idea is you can use the idea is better use the deformed bathy, because it's the reality is that if you apply for a big event using Okada parameters, the most probably thing that you change your floor bathymetry, the bathymeter. So in the last script, you of course you let me move back here. Here. You can use here the deformed bathy in order to calculate the inundation depth. Okay. So, but if you have a very I don't know how to say, a very near fault near to the coast, maybe if you use the deformed bathy, you cannot catch the coast line very well in order to reproduce or in order to plot the satellite image, and maybe you will obtain a gap between your original, your coastline produced after the Okada fault and the coastline that you can see by using the satellite image, but it's just small difference. But you have to take it into account if your fault is very, very near to the coast. Okay.
That's right. When you are in the middle of the ocean, that make no difference. But if you are close to the coast, then it's important to use the deformed bathymetry. In order to take into account this uplifting or downlift of the coast that may increase or enhance or not the inundation. Okay. Yeah. I would like to thank Carlos for the effort of preparing this kind of presentation and course. It is always difficult and hard to do. Thank you very much. And in the meanwhile, if you have some question, we can answer. The material will be available, but not today, tomorrow or the day after tomorrow. And tomorrow we will be talking about meteo-tsunamis. As I said, the first part will be by Claire, and the second part, most on the result and numerical simulation, will be given by Alex. So we see you tomorrow. We see Claire and Alex tomorrow too, and I hope you can take advantage of this training course of ChEESE project. Thank you all. Maria Jose.